Alright, I haven't got the first picture for this, but you can look at it on yours, where there was a ring dropped around a magnet up and down, oscillated between the 2 points A and B, and this is the flux it made as it was going through those points. The resistance is here, so we've been given a resistance. And they want to know the current flowing around the ring from 1 to 1.5. Well, when we have flux, we don't calculate current, but what we do calculate is EMF, which equals N change in flux over change in time. Now the EMF is the voltage. It's a voltage. So if we can get that voltage, then we can say current equals V over R, because they've given us resistance. That's what we're going to do first, and then get that current. To calculate the EMF though, we need to know what the change in flux is, not just the flux, but the change in flux. Change in flux, that's what we're doing first. We're going to do that second, we're going to do that third. So the change in flux in this case between 1 and 1.5, here, between here and here, well the flux goes from that to that. So change in flux is flux final minus flux initial, which is final is 0.6 and initial is 0.2, which equals 0.4 Webers. Now we can calculate the EMF. So the EMF is equal to N change in flux over change in time, which is there's just one ring, times the flux is, change in flux we've worked out as 0.4, and the time from 1 to 1.5 is 0.5, and that equals 0.8 volts. And finally we can calculate the current. I is V over R, which is 0.8 over 0.1 equals 8 amps. Which does seem a bit ridiculously high, but it is the right answer. Alright, use the graph to specify the times after time t equals 0 and before time equals 2, when the EMF around the ring will be 0. Now EMF equals N change in flux over change in times. So the EMF in this case will be 0 when flux isn't changing, and that on the graph is when the gradient equals 0. So where are the points after 2, 0 and before 2? So after here and before here, between those 2 points, where is the flux 0? The flux is 0, sorry, not the flux is 0, the change in flux is 0, so the gradient is 0, is when it's flat. So that gradient's steep, this gradient is steep in the negative direction, it's flat right on top there. It's flat right on bottom there, and it's flat right on top here. So at 0.5, 1 and 1.5, the gradient is 0. This is question 17C. Alright, here's the picture of it again, because this is going to be helpful for this question. When the ring moves towards the north pole, so when it goes from A to C, current flows around the ring. Use a sketch or words to describe the direction of this current. Explain your answer carefully. 4 marks, the big one. Alright, so it says when viewed from above. Here's my man looking down, viewing from above. What I'm going to do is I'm going to draw that. So if I'm looking downwards on the ring, and by the way, whenever we're trying to find the direction of the current, this is always Lenz's law. So looking downwards on the ring, so when it's in position A, the ring is like that. In position B, position C. We have, when we're down here, the field lines come out of the north into the south. So the field lines are going through the ring that way. Looking from above, those field lines are coming out towards him. They're coming out of the page. So they're dots. So when it's up there's a couple of dots, field lines coming out of this ring. When it's in position C, there's going to be more field lines. It's closer to the magnet. So there's more of the field lines. Alright, so the upwards flux increases, doesn't it? The field lines going through that ring in the upwards direction are increasing as it goes from here to here. As it goes from A, the ring goes from A to C. Now Lenz's law says, and we can cross this out, but this is just to help our working. Lenz's law. Well, actually, we'll write the real Lenz's law down, then we'll write the other one. Lenz's law says a current is produced which makes a field to oppose the change in flux. And the way that we did it in classes, I like things the way they were. Now the examiners won't know what the heck you're talking about if you say I like things the way they were, so make sure you cross this out after you're finished, but it helps us to figure it out. I like things the way they were. So this ring liked it when there wasn't much field lines coming out, and now there's a lot. So it's going to want to make its own field lines. I'm going to make green ones to cancel some of these out, so because it liked only having 4 field lines. So it's going to make its own field lines this way, so it cancels some of the ones coming out of the page, therefore going back to the way it was. Okay, so that helped us work out what it was. So once I've done that, I can cross this out. And that just helped me, but it's not part of my answer. I want the examiner's reading. Alright, so it makes that is going into the page, so it's a downwards field. According to this, it makes its own downwards field. It makes a downwards field to oppose this change. How was the downwards field made in the first place? It was made by this current. The downwards field is made by A. Now if I'm going to use my right hand solenoid rule, my thumb wants to point, this is going to be ridiculously hard to draw, my thumb's pointing down into the page, and for that to happen my fingers are curling around that way. So that means it is going in a clockwise direction. This downwards field is made by a clockwise current. It's tough, but it's 4 marks. It's meant to be tough. It's certainly one you want to practice a couple of times. Right, the last one in the set. 17D. Let's just move this back and forth. Right, there's the picture, there's the graph. Use the information from the graph and the table below to show the times when the aluminium ring is located at point A, point B and point C. So when is it located at A, B and C according to this, as shown in figure 22. So when it is, the flux is coming through here, it's spreading out. So when it's here, it has some flux. When it's here, it has lots of flux. And when it's, see these actually, some of these miss, and they end up going around like that. When it's here, it has some flux again. So lots of field lines. See, I've got 4 of them sort of going, will be going through this ring. Up here, I've only got 2 of them, and down here again, I only have 2 of these field lines going through the ring. So some up here when the ring's in this position, lots when it's in position C, and B has some. So if it starts in position A, here's the some flux, and here's lots of flux. So it starts in A, and then it goes to C, and then it goes down to the bottom to B, then back to C, then back to A. So that's starts at A, goes to C, because C's here. A through to C, through to B. So it goes A, C, lots of flux, and then down to B, some flux, then back up to C, then back up to A, and then back down to C again. So when is it at point A? We've got it at point A as 0 and 2 seconds. We've got it at point C as 0.5, 1.5, and 2.5. And we've got it at point B only at 1 second.